A warm welcome here in the CoE company. So first of all, I want to introduce to you Mahdi Salehi. He received his PhD degree in statistics inference from the Ferdowsi University of Mashhad, Iran. It's a very esteemed university. It is, I think, the second highest ranked in Iran. So that, of course, already says a lot. In 2016, he spent a 6-month sabbatical leave under the supervision of Professor Untitled Azzalini at Padua University of Italy. And I think all the statisticians know Professor Azzalini is one of the best in the world. So learning from one of the masters is also very beneficial. He has been assistant professor of statistics at the University of Nishabur, Iran, since 2017. His areas of research as follows is rank set sampling and its variance, flexible distributions, audit data, R-shining web applications. His research portfolio consists of 26 publications and, of course, also book chapters in important statistical journals such as Statistics and Probability Letters, Journal of Computational and Applied Mathematics, Journal of Applied Statistics, and so forth. So a very colorful CV for someone that obtained his PhD only in 2016. So we are really fortunate to have him here today, and we're looking forward to this talk. And I hope that you do have a cup of coffee in your hand. So Mahdi, over to you.
Thank you, Prof. Becker, for introducing me. In the name of God, good day, everyone. I hope you are doing great. So my name is Mahdi Salehi, and today I'm going to speak about clustering via semi-parametric density estimation, which is a joint work with Prof. Becker and Prof. Arashi. Actually, we are going to introduce a semi-kernel density estimation and then apply it in the clustering, in the density-based clustering proposed by Prof. Azzalini and his colleagues. To this end, I've split the presentation into 3 sections. In the first section, I will introduce you about the clustering via nonparametric density estimation, which is defined by Azzalini and his colleagues. And then I will give you some motivation about using the asymmetric kernels. And then from section 2 on, our main objective will start with proposing that semi-parametric kernel density estimation, or KDE, from now on. And then I will go ahead with some details about how to find the optimum bandwidth under the univariate setup as well as the multivariate setup. And then finally, in the last section, I will go ahead with applying our semi-parametric KDE in the algorithm, clustering algorithm defined by Azzalini and his colleagues. So before going ahead with clustering via nonparametric density estimation, let me just have a quick tour about what does clustering stand for. Maybe you're familiar with clustering approach, but let me briefly explain it for you. As you may be familiar, the clustering process aims at grouping together points having high similarity and placing instead those with large dissimilarity in other groups. So if 2 points belong to a specific cluster, they have maximum similarity, and for different points from 2 different clusters, they have maximum dissimilarity. So this is the mechanism behind the clustering. But depending on the definition of the similarity, we may have some various types of clustering. We have traditional approaches, which can be divided into 3 subsections: partition-based, like what we do in k-means and k-medians; distance-based, like what we do in hierarchical clustering; and also grid-based. But the other 2 are a more statistical version of clustering algorithms. Maybe you are familiar with model-based clustering, that here we work based on a fully parametric model, a finite mixture model. And also in the density-based clustering, we work based on kernel density estimation rather than a fully parametric model. So our intention in this presentation is to work based on the last case, which is a density-based clustering. So let me explain the model-based clustering a bit more. In the model-based clustering, as I mentioned, a finite mixture of parametric distributions is introduced. More specifically, suppose that we have a random vector of x, and it is considered to be a mixture of, for example, capital J subpopulations. So its density function can be of this form. As you can see, we have a pi j, which is the relative weight of the component fj. So the number of components, which is here denoted by capital J, is our number of clusters. So in the model-based clustering, the number of clusters should be determined by the user in advance. But how we can how we can assign a cluster to a point. Suppose that we are given an observation like x0. So it's allocated to the cluster with maximal density fj among the j components. So there are some benefits for using this model-based clustering, and it is that this kind of clustering is very precise. But if the shape of the components are, I mean, the FJs are similar to those of the clusters. For example, if the clusters are all symmetric, the finite mixture Gaussian modeling will be working very well. But if the data have some skewness behavior, you should use, for example, multivariate skew elliptical distributions or so. So, but for using this kind of clustering, you should be aware of the shape of the clusters in advance. The other benefit of using such clustering approaches is that there are some very nice packages in R that you can use them. But beside this advantage, there are some potential drawbacks also for this kind of clustering. The first drawback comes from the identifiability problem. Unfortunately, to render the estimation problem identifiable, you need to force some restrictions on your components. So you cannot use every component that you like. Otherwise, maybe you will be exposed to the unidentifiability problem, which is not good for a parametric model. The other potential drawback is that the number of components should be determined in advance. So the number of components will be exactly the number of clusters. So the number of clusters should be determined by the user. So this can be a potential drawback. Why the potential drawback? Since for estimating the optimum number of clusters, you need to do some further computations. The other point comes from the shape and matching the shapes of the cluster, as I mentioned before, with the shape of the components. If the cluster shapes do not match the ones of the components of J's, then the model-based approach may face some difficulties. So these are some drawbacks for this model-based clustering, which seems to be a fully parametric model. But on the other hand, we have the density-based clustering. In the density-based clustering, the things are different. The mechanism behind the density-based clustering is associating groups to the connected regions of the density. This figure illustrates what I mean. Suppose that we have a univariate data set and the fitted density is this solid curve. So first of all, this algorithm, the density-based algorithm, finds the number of modes. So the number of modes here correspond to the number of clusters. But the difference between this algorithm and the previous one is that here the number of modes or the number of clusters will be automatically detected by the algorithm itself, not by the user. So this can be a potential benefit for this algorithm. And after obtaining the number of modes, this algorithm will assign the points surrounding each mode to specific clusters. But it seems that the estimation procedure of our density being estimated is very important, plays an important role. So one of the approaches of in estimating the unknown parameter, unknown density of the population is to use the kernel density estimator that you may familiar with it. But let me explain it for you briefly. Suppose that we have a random sample of size n from a density function f, then the KDE or kernel density estimator evaluated at x is obtained as this formula. As you can see, it's something like a sample mean. H here is called the bandwidth, or sometimes it is called the smoothing parameter, which plays an important role here. And also we have a kappa, which is called the kernel. The kernel is typically used to be a symmetric function, a symmetric density, like the Gaussian kernel, but not necessarily. Okay, so the non-parametric PDF cluster, which is this one that I explained it for you, is proposed by Azzalini and Toreli for the first time in 2007. They actually used the KDE for estimating the density of the population. They exploited the spatial tessellation, which is a spatial notion, to generalize the concept of adjacency among points in several dimensions, which is a very difficult step here, and determine the connected level sets. And then clusters are associated with the maximally connected components with estimated density above a threshold. But there is a problem here. Their algorithm was not feasible when the dimensional space is high, for example, more than 6. So they improved their method in 2014. So Menardi and Azzalini found a viable solution to this problem. Fortunately, both methods, I mean the one which is proposed in 2007 and the other one which is proposed in 2014, both methods are aggregated in a unique algorithm and are implemented by the R package PDF cluster, which is a very nice package by Azzalini and Menardi, which is published in the Journal of Statistical Software. So this is the non-parametric PDF cluster. Why I have used the non-parametric term for this PDF cluster algorithm, since it uses the KDE, which is a non-parametric approach in nature. So from now on, I use the non-parametric PDF cluster for the algorithm defined by Azzalini and his colleagues. Okay. In summarize, if you want to compare the well-known clustering approaches, we can say that in the partition-based clustering, like what we do in the K-means, first of all, we need to determine the number of clusters, which is potentially a drawback. And also the other drawback is that here, the number of the initial points are selected randomly. So if you implement this algorithm once again, you may will be exposed to another result, which is not that much good. In the distance-based clustering, you have such a dendrogram. For example, in the hierarchical clustering, we are exposed to such a dendrogram. Here, the number of clusters are left undetermined, and it will be selected by the user. So you need to cut this tree at a specific height, and then you can obtain your clusters. So here, the number of clusters is also undetermined. So you as a user should determine it. We spoke about the finite mixture modeling or model-based clustering. And the one that I want to use it is the density-based clustering that you can see one of its examples here. In the density-based clustering, as you observe, the number of clusters, which are the number of modes, is automatically detected by the algorithm. So it's an advantage for that. So now I'm going to give you some motivations for using asymmetric kernels rather than symmetric kernels in some specific situations. You know that classical kernel methods are based on symmetric densities, typically, say around 0, as in the case of the normal kernel. But there is a deficiency here. The deficiency arises by using such kernels, I mean the symmetric kernels, when we try to estimate densities which their suppers are bounded like a beta distribution. The problem is that such kernels assign some weights outside the boundary, which is not desirable. On the other hand, the asymmetric kernel methods never assign weight outside the density support. So they effectively tackle to the boundary bias problem. The other point comes from the sample size. The density estimators in small sample sizes or moderately sized samples tend to inherit some prominent properties of their kernels. Thus, if a density is suspected to be highly skewed, it makes sense to utilize asymmetric kernels, not the symmetric ones. Otherwise, you will have not good fittings. So in these situations, we can use, it's better to use the asymmetric kernels for the KDE rather than the typical symmetric kernels. So our main objective here is to propose a semi-parametric PDF cluster. A semi-parametric PDF cluster. Our main goal actually in this work is to improve the density estimation part of the PDF cluster algorithm, not the whole algorithm, just the density estimation part of the PDF cluster, of the non-parametric PDF cluster algorithm of Azzalini and his colleagues, by utilizing some skew symmetric kernels rather than just symmetric kernels, which used by Azzalini and his colleagues in their algorithm. They use just the normal kernel and the T kernel, and they didn't use any skew symmetric kernels like what we want to do now. So what is the skew symmetric distribution? As its terminology, the skew symmetric or skew modulated sometimes distributions can generate both of symmetric and asymmetric densities. You can study this paper for more details. Among so many distributions belonging to this family, we selected just the skew normal and skew T distributions as its most well-known members. So they are flexible enough to be employed as a kernel in the KDE. Maybe you ask me that why you don't use any more sophisticated member belonging to this class. For example, scale mixture family of distributions or something like this, maybe some more sophisticated skew elliptical distributions. And the answer is that we are going actually to propose an algorithm which is something between this one and this one. It's something between a fully parametric model, which is handled by the model-based clustering, and a fully non-parametric model, which is handled by the density-based clustering. By this manner, we have gathered the precision of the fully parametric distributions of the fully parametric models and the flexibility of the non-parametric models. So let's see what will happen. Okay, so now I'm going to introduce you our main objective, which is introducing a semi-parametric kernel density estimation. suppose that we are exposed to an n by d matrix of observations. So we have d random variables, which are located in the columns, and we are going to cluster them to make clustering, apply a clustering algorithm on these matrix. Azzalini and Menardi in 2014 performed the density estimation step of the clustering algorithm by the kernel method, employing a product kernel estimator like this one. You know that Hij is the members of the matrix of the bandwidth, and the kappa is our kernel, and Azzalini and Menardi use the normal and the T densities as this kappa. But here we intend to employ a product kernel of this verb. There are two differences between this one, I mean the formula 4 and the equation 3. As you can see here, the kappa is the same for all of the variables, for all of the dimensions, I mean for all j. But here, we allowed the kappa to vary from each column to the other one. So this makes some flexibility on our estimated density. The other point is that here, we have used the skew normal and the skew T densities as our kernel. And you know that the skew normal density, which is this one, and the skew T density, which is this one, include the normal and the T distributions respectively. So here we have the kernels used by Azzalini and his colleagues, plus some other asymmetric kernels as well. The other difference between this product kernel and the previous one is that this one, which used by them, is fully nonparametric. Here there is no noisance parameter to be estimated, but here we have some noisance parameters and we have to estimate them. For example, if you select the skew normal as your kernel, you have d lambda, d slant parameter. So you need to estimate them. And if you select the skew T as your kernel, you have 2 times d noisance parameters to be estimated, since here we have the degrees of freedom as well. Okay, so we need an algorithm for the estimation procedure. So just follow this algorithm. First of all, you can standardize the observations of any variable that you have. Here we have d variables, so we need to standardize them. I mean, just subtract any observation from each column by its average and then divide by its sample standard deviation. So we have Zj for the xj variable. Then you need to choose between the kernels, whether I'm going to use the 5 or the 6, I mean the Sn or the St. And if you selected the Sn normal, you will plug in the lambda j's involved with its MPLE, which is maximum penalized likelihood estimation, assuming Zj is a random sample from the skew normal distribution. But why MPLE and why not using the MLE itself? Maybe you know that there is a peculiar property for the slant parameter, I mean the lambda parameter in the Sn distribution. And the point is that sometimes the MLE will diverges, while it is not an infinite value in the reality. And this event occurs when all of the observations are positive or all of them are negative. So all of them are equal sign. And this event has non-negligible probability when the lambda is a large value or the sample size is small. So we should tackle to this problem. Azzalini and Toreli in 2013 propose an approach for tackling this problem, which is penalizing the likelihood function of the square normal distribution. And the estimator is called MPLE. Fortunately, there is a routine called sn.mple in the well-known SN package that you can use it. And it automatically assigns some good initial values for running the chain. So no worry about the optimization procedure. But for the SD kernel, the things are a bit different here. Since here we have the degrees of freedom as well. So since here the nuisance parameters are more than the one in the SN kernel, we need to be careful. If we are exposed to high dimensional spaces, it's better to use an approach, an estimation approach, which is not that much computationally expensive. But fortunately, there's no problem here as well, since we have a preliminary estimates by using the st.prelim fit in the SN package. And this preliminary estimate proposes some very nice initial estimate for the parameters of the univariate as well as the multivariate skew T distribution. If you want to see the details of this routine and this paper, you can go ahead with the paper by Azzalini and Toreli in 2020 that you will see in the references. But for the low dimensions, we have time to select some more computational algorithms. So here we can use their MPLEs exactly like what we did in the SN. And here we can use the st.prelim fit as the initial values of the MPLE. So this hybrid procedure will work very nice. You will see. So everything is now completed, and we have estimated our nuisance parameters, and then we can compute our f hat of x in 4 that you remember with kappa j, whose nuisance parameters are just estimated. So the only thing remained is to find the optimum bandwidth, an optimum bandwidth that I will show you in the next section. So how we can find the optimum bandwidth? To make simplify the things, let me start off with the one-dimensional case, and then I will go ahead with the generalized version, which is multivariate case. Suppose that we have a univariate density function like f, and we are going to estimate it using the product kernel. Of course, since we have just one component here, one variable here, so just we have a scalar, not a product. So assume further that our kappa is a one-dimensional asymmetric kernel. I mean, a skew symmetric kernel density satisfying this regularity assumption. Our kappa should be a non-negative function for all of the z belonging to the real line, and its integral should be equal to 1. So these two conditions implies that our kappa is a density function. So this integral is its first moment, which is not necessarily equal to 0, since it is not necessarily a symmetric distribution. So for obtaining an optimum bandwidth, as you know, we have some approaches. One of the approaches for obtaining the optimum bandwidth is to obtain it via minimizing the AMIST index. AMIST stands for approximated mean integrated square error, which can be used for comparing some kernel density estimators. So there is a very big story behind this formula. I just bring for you the results. So the optimum bandwidth can be obtained from solving this nonlinear equation. And as you can see, its constants are functions of n, which is our sample size. So we have it, our lambda, which is our slant parameter under the Sn density, and also our sigma. Sigma is the standard deviation of our population. So we need to estimate these parameters. So we have two kinds of parameters. The parameters belonging to our population, which is sigma, the parameters belonging to our kernels, which is lambda here. We estimate the lambda as what we did in our algorithm, and we can use, we can plug in the sample version of sigma, I mean the S, as the sigma. And if you want to have a more robust estimator, you can use, for example, interquartile range. So we have no problem here since we have estimation of lambda and sigma. Now I'm going to check out the behavior of our optimum age with respect to the lambda. This is the result. I've included, I've done this comparison for some various sample sizes, which ranges from 20 up to 200. And these solid lines correspond to the optimum bandwidth under the Sn that we just saw. And the dotted lines are the optimum bandwidth obtained based on the normality assumption. So first of all, you can see that when n increases, the number of our optimum age will decreases, as we expected before, since our optimum age here will be obtained in the order of 1 over n to 1/5. So we expected this behavior. The other point, the other interesting point is that when lambda is equal to 0, the optimum age obtained based on the Sn will be exactly coincided to the one of the normal density. So we know that if we put the lambda in the Sn equals 0, it will simplify. It will be simplified to the normal density. So we expected this behavior as well. But the main thing is that here, as you can see, the optimum bandwidth is slightly lower than the one of the normal density, and this is desirable. Just look at this screenshot of the paper by Azzalini and Toreli in 2007. They have written that empirically, they mean that in the clustering step, it was observed that it is often advantageous to shrink age slightly towards 0 in the subsequent numerical work, which is clustering approach. We adopted a shrinkage factor of 3 first as an overall reasonable choice, and our optimum bandwidth is already shrink and does not need any other shrinkage factor like the 3 first. So this is a good news for our semi-parametric kernel density estimator. But what about the multidimensional case? Now assume that our F is a divariate density. Then you know that the kernel density estimator in its most general form is defined as this formula. Here H is our bandwidth matrix, and K is our kernel. But here in this presentation, we restrict ourselves to a special case of this general form, which was given by for, as you know, our product kernel. So under this assumption, I mean by using the product kernel that you saw in equation 4, you can obtain the AMIST of f hat of x as this formula. As you can see, it is a function of sigma j, and sigma j is the standard deviation of xj, which is our j variable, and also to the d is the number of dimension. For example, if we have a bivariate case, d will be equal to 2, and it is also a function of mu1 and mu2, which are our first and second moments of our kernels. And since, of course, they are functions of the parameters involved by the kernels. So here also we have two kinds of nuisance parameters to be estimated. For the parameters involved by the our kernel, we use our algorithm, and for this sigma j, we use their sample versions, sample standard deviations or so. So by minimizing this equation, we will be exposed to such an equation. So our optimum h will be obtained as the root of this nonlinear equation. And the interesting thing is that if you put the d equals 1, this equation will be exactly the same as this one that we saw in the univariate setup. Okay, now I'm going to check out the behavior of the optimum bandwidth in the multivariate setup as well. We saw something in the univariate setup, but here I'm going to check it out for the multivariate setup. In order to be able to visualize the plot, I obtained the d to be equal to 2, so we have a bivariate case. So since d is equal to 2, we have two kappa 1 and kappa 2, so we have two lambdas, lambda 1 and lambda 2. So now we can sketch the surface plot of our optimum h versus the pair of lambda 1 and lambda 2, considering the identity for our standard deviations. In the left panel, illustrates the one for n equals 50, and the right one is the result of the n equals 200. As you can see, the right one is less than the left one, which was expected before. And the other point is that the behavior of the surface plot here is exactly the same as the univariate version. You can see that when we go to the 0, I mean, when the lambdas go to the 0, we will have the maximum for our optimum h. So everything is the same as the univariate case. Okay, now we are going to test our semi-parametric kernel density estimation on data. To this end, I've simulated a sample of size 500 from two subpopulations. Sorry. And both of the subpopulations are skewed. You can see that all of the 4 kernels have had good fittings on the data. But the asymmetric ones, I mean the bottom 2 panels, have had better fittings. You can see that there are big empty spaces here, while here fittings are less than the response. So our next question is that whether this goodness of fit of the asymmetric kernels will impact to the clustering step of the nonparametric PDF cluster defined by Azzalini or not. So let's see. One thing is that if you remember, we had 2 approaches for estimating the parameters of the ST kernel. The left one is the one used, the MPL is, and the right one is the one used ST vector. As you can see, both of them have had good fittings, but you will see that if you use the MPLE, which is of course more precise, it has more better results in the clustering step. So I recommend you to use the left one, I mean the MPLE one, rather than the ST vector fit if you have a small dimension. Okay, last section is introducing about the clustering via semi-parametric density estimation. So before going to our algorithm, which is called here semi-parametric PDF cluster, let me back once again to the nonparametric PDF cluster. The non-parametric PDF cluster of Prof. Azzalini and his colleagues has two main stages. In the first main stage, they construct a cluster tree and then obtain the initial clusters. As you can see in this example, we have four clusters. We have four distinct clusters here. And in the first stage, the algorithm has detected the initial clusters, but the point is that we have still some points which are not allocated yet. So this is why we need to go to the second step, where we can allocate possible unlabeled points to the clusters formed by this step. The right pane illustrates step 2. You can see that all of the points now have allocated to the right clusters. But the good news for us is that in both of the steps of the non-parametric PDF cluster, the estimation, the kernel density estimation, plays an important role, and it is used. So our intention is to plug in our semi-parametric kernel density estimation with the non-parametric kernel density estimation used by them. So we are curious to see the results. So this is why we have named our algorithm by the semi-parametric PDF cluster. Okay, so let's back once again to our data. If you remember, we fitted our kernel density estimators using all of the four kernels, and now we are going to see the impact of using the skew symmetric kernels. As you can see, all of the four kernels have had good clustering results for the points that are strictly distinct. But what about the points which are near to the boundary, like these 2 points, maybe these 2 points, maybe this one, maybe these 4 points? So we need to have a numerical index in order to compare the densities. So to this end, I've obtained for you the contingency table of the true partitions. The rows are denoting the true partitions, and the columns are denoting the clusters that we obtained based on the density-based clustering for all of the normal T with 7 degrees of freedom, which was used by the Azzalini and his colleagues, and our proposals, which are SN and ST, and for the benchmarking proposed, we have also included the k-means as the traditional approach, as one of the traditional approaches in the cluster. You can see that, so under the definition that I told you, so the diagonal entities show us the number of points which are allocated correctly, and the off-diagonal ones are the number of points, are the number of mistakes. So you can see that the number of mistakes in the k-means is 8. The number of mistakes in the normal is 8, while it is 9 for the T7, and it is 5 and 4 for the SN and ST respectively. So based on the contingency table, our proposals, our kernels, which were asymmetric, have had better results comparing to the other competitors in this example. If you want to have just one number for the ease of comparison, you can use the ARI, which is the adjusted rand index. This is an index which can be raised up to +1, and the bigger values correspond to the better models. You can see that the ST and the SN have the maximum value for the ARI. So we can say that in this example, in this situation, that you are exposed to skew data, you are recommended to use the SN and the ST kernels as the normal and T7 as your kernels. Thank you very much. And these are some references. If you want to have some details about the MPLE, you can study this reference. And for the kernel density estimation, you need to study Azzalini and Toreli in 2007, and also Azzalini and Menardi in 2014, the Journal of Statistical Software 1. And for the Stida-Trilling fit, you can go ahead with the 5th reference. And these are the rest of the references. And thank you so much for your attention.
Thank you so much, Mahdi, for a very interesting talk. So let us hear from the audience if there are any questions. You can also put some questions in the chat.
Andrea, there is a question in the chat from Mohammed Arashi.
Okay, thanks a lot. Let me see. Yes, Mahdi, future directions, let us hear. Mahdi?
Yes.
Yeah, and this, yeah. So Prof. Arashi wants to know if there are, what is your future plans? And then there's a question also from David Rose. Why 7 degrees of freedom for the T distribution in this cluster?
Our future plan is to generalize this algorithm to the Bayesian viewpoint. Yeah. What was the next question, Prof?
And the next one was, why 7 degrees for the T distribution in the PDF cluster?
Yes, the T7, the T distribution with 7 degrees of freedom is used by Azzalini and his colleagues in the PDF cluster package. And you should ask from Prof. Azzalini why 7 and why not 6 or 8. So this is not.
With Prof. Azzalini.
Yeah.
It's also for comparison, you know, and stuff. Yeah, so it is good. I don't know. Mark has a question. Can you see it? Do some points remain unlabeled? Is there a reason why some of the crosstabs at the end don't total to 500? Did you hear me, Mahdi?
Yes.
Yeah. Must I repeat the questions? Must I repeat it? Do some points remain unlabeled? And he also asked, is there a reason why some of the crosstabs at the end don't total to 500?
Yes, it's true. Maybe there is some typo, yeah. But if you go ahead with the ARI, you can see that the SD and the SN have maximum value for the ARI. So I need to double check these numbers. Thank you for the response.
Yeah, that's a good remark. But also you ask, is there still some points that are there still some points that remain unlabeled with this approach?
Unlabeled?
Unlabeled, that you do not, you know, where it belongs. That is not in a cluster.
This one, you mean?
I don't know. Mark, and maybe you can put on your mic and also ask for more clarity.
Thank you, Prof. Sorry if there's background noise, I apologize. It was in relation to the crosstab tables. I was just wondering if maybe they didn't total to 500 because some points weren't actually given a label, but maybe it's just some side.
Maybe because we have to double check. Thank you for that observation. Because the paper is under revision. I think we submit the paper, isn't it, Mahdi? Paper is,
yes.
Yeah. So we must just double check. So that we have
it's just a typo.
It's just a typo. Yeah.
As you can see, after doing the second step of the PDF cluster, then all of the points will be allocated to the right cluster. So no point will be remain unlabeled. So that is just a typo.
Any other questions? There's a question from Anapura. How well do this algorithm work for spiral-shaped clusters? Mahdi?
I've not tried for spiral-shaped clusters. Let me try. I don't know.
Yeah, we never know.
Yeah.
Very good suggestion. We don't know.
Thank you.
Thank you for the remark. We are always open for, you know, it's nice to see how other people think, and then we can also think, and it's very nice, this sort of networking or comments is very welcome.